This video is about Jim Cline's trip and presentation of his fourth formal presented technical paper on his KES to GEO concept at the American Society of Civil Engineers Space 2004 conference held in League City, Texas, March 7th through 10th, 2004. 7 years ago, in 2004, I created my fourth formal technical paper about my KES to GEO ground high Earth orbit concept, which is an unusual electrically powered transportation system, conceptual design, to provide a walk-on equatorial ground, walk-off in facilities in a geostationary Earth orbit capability for civilization's expansion, titled Energy Flow and Kinetically Strengthened Transportation Structure Systems to Space. It was published in this book starting on page 859. This shows a couple of pages in the open book. As a brief overview, to be clarified later here, it would be an immense perimeter, 131,000 kilometers around, hoop-shaped synchronous electric motor structure, whose weight would be supported by mass streams flowing along inductive tracks inside it, at velocities several times orbital velocity of that particular trajectory. The excess centrifugal force acts to balance the weight of the stationary part of the structure that contains the tracks, along with using some of the upward bound energy of the high velocity mass to drag payload carrying captive spacecraft along exterior maglev tracks, using electrical energy to lift payload, including construction materials and people, from equatorial ground level of the Earth up into the geostationary Earth orbit. And several enabled applications are part of the integrated conceptual design, as will be described later. My last technical paper's presentation to the American Society of Civil Engineers was given in March 2004 at League City, Texas. As were all my technical papers in the presentation, it was all done on my own time, at my own expense, and was ever a fringe area dominated by large corporate interests, plus some published or perished papers by students, and a few like me, independent thinkers with ideas to share. Here's a quick version of that effort, the journey there and back, and the presentation itself, as best I can reconstruction the verbal part made for the presentation itself. I wrote this technical paper on my little iBook and created it as a camera-ready copy and created the PowerPoint presentation on the little computer too, and it ultimately was used to give the slide presentations itself at the conference. It was a long drive from the Los Angeles area to League City, Texas, across a lot of desert. The rest stops were very welcome on this long drive. One of them had some very pretty flowers alongside it. It seemed that Interstate 10 was designed just for this trip. Here's an interesting overpass in the making, speaking of bridges. Since this was on my own nickel, I had to get a cheap motel room in off in Lake City itself. Here's a picture of me there. After registering at the conference, I got my speaker's badge as well as a copy of the proceedings with my paper in it. And here's a self-photo in the mirror in my motel room's mirror. And this one shows my little notebook carrier with my introduction card on it, as well as the new book. Here's a view at the conference site across the marina that was adjacent to the conference building. And here is the building in which the conference itself was held in Lake City, Texas. And another one of those self-photos in the mirror. I had no one to help me, so I got a lot of this kind of thing. Here's my car in the parking lot with the reflection in the mirrors formed by the windows of the conference building. Here is one of the stands that identified where the American Society of Civil Engineers sessions were being held. And this one shows part of a room that was beyond it. There were a lot of mirrors in the architectural design of this impressive building, so I could get my own picture taken several times. And another one. Break times had a refreshment area in this room where you could get coffee or soft drinks and take a break for a while. The Steuben room was the one where my presentation was made. Another picture of the identification on the door of the room. Here's what the room looked like inside, even though this picture was actually taken just after the end of my presentation and several others at the same time. My presentation was scheduled to be at the very end of the conference, and in fact, due to delays, the conference already was over before I got to give my presentation, so perhaps some people will finally be able to get to see it if they happen to find this video. I started off my presentation with the question, can there be two bottom lines for corporate decisions? One for the early profit for stockholders and the other for the survivability of mankind as part of the complex biosystem web of the Earth life. And so I set the stage for a wide focus viewpoint for a generalized map before shifting to immediate specific goals for integrating space resources. Our highly industrialized way of life, for which we ought to be responsible, depends upon plenty of energy for our voracious technological systems. Throughout history, when put to the test of depletion of natural resources of shelter, nutrition, or fuel, mankind has survived and thrived by building new kinds of support systems. Another such test is rapidly upcoming when the exponentially rising worldwide demand for energy crosses the production from normal petrochemical sources. I hope to convince you that given the will to do it, it is possible that the aerospace industry can enable the supply of the projected 550 megawatt of electrical energy generation capacity increase per day in the world's industrialized nations, a 2 terawatt increase per decade throughout the current century, by utilizing dynamic transporting structures sustained by energy stored flowing within themselves to abundantly access space, initially for emplacing materials for constructing and maintaining the necessary satellite solar power stations in geostationary Earth orbit, even enabling elegant total recycling systems for clearing out the industrial waste products, all sustainably solar powered. The target here is to quickly create a working space access transportation system that is fully adequate to the huge task. The transportation system is integrated with the many applications it enables. It lifts payload carrying spacecraft between ground and high Earth orbit, geostationary Earth orbit, where payload will stay with little further added energy. It lifts by means of the spacecraft electrodynamically braking against a very fast upward moving stream of electric motor armature segments along the orbital transfer trajectory path of the spacecraft. And the mass streams move within a structure that is supported and largely shaped by the kinetic stator of the counter-rotating mass streams containing electric motor structure. And this transportation system that, after a couple metaphoric stages, supplies all of its own transportation energy from the solar satellite power stations it puts in geo, thus independent of ground energy sources from then on. The transportation technologies that are involved are not that strange. It's fairly conventional, except not used in this configuration, and the potential benefits are very interesting and potentially very profitable. Consider that the directed flow of stored kinetic energy within a structure has the potential for drastically changing structural potentials, including enabling an immense size. For comparison, recall that pressurizing a collapsed limp preformed bag can transform it into a large complex structure that has predefined shape that resists deformation. This is a non-directed stored kinetic energy structure. Whirling a limp rope to form it into a circular shape that resists deformation, a lariat, is an example of the directed flow of kinetic energy. Using an advanced form of electric motor technology, directed flow of kinetic energy may enable creation of a hoop structure around the Earth, eccentric from the equator up to geo, which will lift payload between ground and geo, massively opening up space to civilization in our time. Let's think again about the basic energy given only to the payload mass by lifting it from the equator up into geo, which is 5.7 times 10 to the 7th joules per kilogram. In high contrast to the extreme amount of launch vehicle chemical energy now required to put payload into geo, the work done only to that payload by moving it from the equator up to orbit in geo is only 5.7 times 10 to the 7th joules per kilogram, or 15.7 kilowatt hours per kilogram, which at an energy cost of 10 cents per kilowatt hour is only $1.57 per kilogram to geo. Anywhere near this cost of access to space could totally change civilization's relationship with space and its resources, a worthy goal. So to create an adequate transportation conceptual design, let's start with the workable parts of the 1980s concepts of Keith Lofstrom's launch loop, Rod Hyde's Starbridge, and Earl Smith's Texas Universe Railroad. Then fill in the missing pieces for an integrated transportation concept targeted to be potentially adequate to the task of providing the massive and inexpensive electrically powered transportation to move civilization solidly into space and high Earth orbit within a couple of decades, if we wanted to do that. As youth, my cousin and I, Howard, already thinking about how to access space, calculated the belts and pulley ratios necessary to spin a gyroscope circumference at escape velocity, starting with a powerful 3,600 RPM electric motor. Rigged up in their barn, the belts and pulleys slipped and howled as they strove to do the task. Then we discovered limits to the tensile strength of materials as the gyroscope explosively vanished in front of our eyes, along with simultaneous, very worrisome loud bangs throughout the walls of the barn. In the case of a kinetically supported transportation structure to geo, the Earth's gravitational field does the bending function instead of tensile strength of materials. The armature segments traveling at tens of kilometers per second as they pass by the Earth's surface terminal in the evacuated tubing, along a path that resembles an orbital transfer trajectory between Earth radius and geo radius. The velocity of those armature segments is chosen to be sufficiently faster than orbital transfer velocity of that path that they're constrained to, that the resultant outward centrifugal force presses upward against the tubing and sliding track structure so as to essentially balance the force of gravity on its mass, thus supporting its weight with its live loads all the way between ground and geostationary Earth orbit. The armature segment mass stream sliding very fast on magnetic levitation tracks in a hard vacuum along a track-constrained path could store and distribute energy, transfer momentum into vehicles, and exert forces to shape a structure. The induced magnetic field increases with the square of differential velocity, and tens of kilometers per second is a lot of differential velocity. Only vaguely similar to that used on today's massive maglev trains, this is technology needing rapid exploration, requiring a hard vacuum environment for the experiments. Those armature segments electromagnetically coupled to the tracks in which they slide at high velocity, and also to the upward bound portions, also couple into the inductive field of electrodynamic brakes of spacecraft, riding the structure upward, transferring momentum. The primary payload lift mechanism occurs when some of the system-wide stored armature mass stream kinetic energy is inductively tapped off to lift spacecraft vehicles up the outer maglev track structure between ground and geo and back. Besides lifting of payload-carrying spacecraft up to GEO, some of the stored electromagnetically coupled kinetic energy is consumed through electrodynamically braking for servo positioning of the structure to compensate for wind and other loads. Unequal velocity, contra-rotating mass stream pairs, and solar-powered mass thrusters located below GEO on the KESS contribute to the overall structure, maintaining 24-hour synchronized rotation with Earth. The armature mass stream's outward centrifugal force is greater than that necessary to exactly balance the weight of the stator and live loads for structural position stability, the extra load being taken up by tensile strength of the stator materials. Again, let me point out that the geostationary Earth orbit bound payload carrying vehicles inductively brake against the upward bound armature mass streams, thus lifting them from the ground to GEO without need of onboard fuel or external beam laser power. Electrically powered synchronous mass drivers at the ground terminal, such as located in a tunnel in the Ecuadorian Andes Mountains, replenish the energy consumed within the KESS structure and by its continuous lifting of payload to space and back. After being placed in GEO by the KESS, satellite solar power stations supply this energy to the mass drivers, thus greatly improving chances for very long-term sustainability of large-scale space access in an otherwise potentially impoverished world of political unpredictability. Such a transportation structure has potential for aerospace to solve many severe problems that civilization is beginning to face in crisis, while also enable orders of magnitude increases in worldwide commercial business through huge access to abundant nearby space resources. Their transportation capacity and efficiency may far exceed that of nuclear rockets and anchored tether space elevators. They could enable construction of 2 terawatt per decade of satellite solar power stations in geostationary Earth orbit to solve much of the world's energy crisis. They could enable construction and use of immense solar-powered mass-charge ratio toxic wastes, total recycling plants in GEO, solar-powered, applying negative entropy to wastes. They could enable the major spaceports to be moved up to GEO, 91% up out of Earth's gravitational energy well, a great head start for the large spacecraft to the Moon, Mars, and asteroids, and far beyond. This block diagram shows the energy flow in a fully operational KESS GEO, expanded to full capacity and moving payload carrying vehicles to and from GEO. Over in the upper right, the multiple solar power stations receive solar energy, is beamed to ground to power the KESS and supply electric power worldwide. Electric power is supplied to commercial power grids worldwide, adding 2 terawatts capacity per decade. Solar-powered satellites provide all energy needed to replenish energy supporting the KESS structure itself. Solar-powered satellites provide all energy used to power the KESS to lift construction materials and facilities to build multiple facilities in GEO. Much of the energy from the returning spacecraft also goes back into the system, and much useful energy is provided. In summary, our industrial civilization, including population, has rapidly expanded the utilization for our finite inexpensive energy sources. Now we need to find ways to efficiently replenish them. This finite energy supply appears to soon be inadequate for the worldwide civilization's growing demand. Solar power satellites and GEO can solve this problem was proposed 40 years ago and had waited adequate means to build them in geostationary Earth orbit. With the transportation system proposed here, there appears to be a way now to create a transportation system adequate to transport the materials to build and maintain abundant satellite solar power stations in geostationary Earth orbit out of Earth's surface materials, and do it economically and quickly. The system uses an unconventional combination of existing civil, electrical, and aerospace engineering principles composed into a different technological configuration than is used by today's business. It would create lifting bridge structures supported by internal energy that would lift spacecraft with payload up into geostationary Earth orbit and back along orbital transfer trajectory shaped paths that actually are not quite elliptical. This also could enable the massive expansion of civilization into a second level up into geostationary Earth orbit. Passive matter there soaking up the trapped radiation. We could also have the total recycling of toxic materials of very high spaceports. The construction of the 1975 design Stanford Torus type 10,000 person each space habitats for increasing lots of room for people to live, and with easy commute to ground along the KEST structure. Can the world of people interaction momentum, including our struggling aerospace industries, be turned toward this new direction of KEST to GEO long before the energy systems are spent and we are locked onto the ground? It would be preferable to maintain the momentum of an inexpensive, clean energy supported industrial civilization, and this concept presented here has the potential of doing that. You can check out more information about this at the www.kestsgeo.com website and see what's happening new. That ended my presentation, and not too much to my surprise, I got glares from the other people there. The conference soon ended and people walked out, nobody ever talking to me again. And here's the room a few minutes after all that happened, a couple people just about to leave. Having done my best, I got myself out of there and walked back to my car. Here I got a self-photo of myself. To brighten up the situation, there was this pretty flower. The long journey back across Texas started up. I was back on the road again. I stopped again at the rest stop, which had the large wagon wheel symbol of transportation and wheel structures. It seemed to be appropriate to this occasion, so here's a self-photo there. And the road went across the Texas deserts, and storm clouds helped decorate and cool the trip. Here's another self-photo at one of the rest stops. And into California, or headed there. Here's a sign along the freeway. Here's a nice ocotillo that's in bloom. Getting across the width of California. Here's a map at a rest stop along the way. Coming across the path into LA, we can see the big wind turbine towers that are helping get a little bit of green energy. Back from the trip, I got a photo of the conference proceedings book with the sack that I carried it in with. I was soon back doing my volunteer work at the Natural History Museum's invertebrate paleontology facility, doing the making of thin sections of coral fossil sections. Here's a microscope. Again, I'm Jim Cline, and I hope you've had some interesting moments watching about this presentation of a potentially very helpful concept of transportation, the idea of a structure that can be supported by its energy that's stored within itself, and use some of that energy to lift material up and down it to very great heights around the planet, including enabling building solar powered satellites and other facilities up there that could make our continued existence on this planet and beyond far more likely to be sustainable. So again, I hope you having a good day and enjoyed this.